we're going to talk about how to hack, or even how to design, or how to check, how to test your cryptographic protocols using formal methods. Anyone here with some kind of experience using formal methods? Anyone knows what formal method is? Good, so I saw a few people. All right. So let's begin with this protocol over here. We want to know if it's safe. Basically, this is what we want. We want to know if this protocol is safe because we were going to release it out. And I'll go quickly describe the protocol for you guys. So we have Alice and Bob. In this case, it could be that Alice is a user, Bob is a service, and Alice sends a message to Bob. Look, this is my nouns. This is me, my identity. Identity, sometimes we send just a certificate, and we encrypt it using Bob's public key. All right? This is the message. Bob gets the message and returns the response to Alice. Look, this is your nouns. This is my nouns. I encrypt everything with your public key. So basically what we did here is that Bob proves that he has the private key, meaning he is Bob, right? Because he managed to decrypt the message. He took the nouns, he sent it back, so there's no even replay attack because this is a nouns. Nouns is a one-time token that is generated randomly. So he sends back. This is what we call challenge response. Okay, so the challenge is let me see that you can decrypt it and send me the response. So so now Alice sends back again a message to Bob. This is your nouns, and I encrypt it using your public key. This is to prove, Alice proves in this way that she actually has the private key, therefore she is Alice. So the question here is this protocol safe? How many people think that this is safe, a safe protocol? Nice. How many people think that it is not safe? Okay, I'll ask you later why do you think it's not safe, but this is basically the question. So the agenda for the talk today is there will be introduction. I'll talk about myself, where I'm coming from, what the goals and the subject and the scope of the presentation. I'll introduce the problem that we wanted to talk about here today, the suggested solutions using formal method and model checker. And then I'll show samples of two tools. I hope I have the time. It's as I said, it's very packed, so I'll really try to run briefly through everything. So I hope to be able to show you demos on Avispa and Tamar Improver. These are two model checkers tools. Then if we have the time, we'll talk about the next steps, what even more advanced than that, and summary. So introduction about myself. I lead the product security at CyberArk. I have 10 years experience in cybersecurity. Before that, I have another 10 years of experience with development and architecture. And 3 years after that, I was working on formal method projects, basically creating tools, what we call for provable software. We want to prove the software that is doing what it should do and doesn't do what it shouldn't do, using automatic tools that can learn the software. And today I'm combining this provable software experience with my cybersecurity experience. We're going to see cybersecurity, provable cybersecurity, basically. And this is also goes together with my passion for cutting-edge technology and cybersecurity. And if we don't have time at the end, I'm sorry, please keep your questions to the end. I hope we'll have time. If we don't, these are my contacts. You can always reach me, and I'll be happy to help and to answer your questions. So the scope for the presentation, because this the scope of this field of provable software and formal method is huge. We stay very high level here. I'm going from down to the top for some reason. So we stay at a very high level. This is only to show you so you can be familiar with the subject. If you want to learn more and to go further with this, I'll be happy to help and later on. And so you can also recognize the benefits of using formal methods in order to test, design, or even hack, if you want, protocols that look very safe, like the one you just saw. We will be talking today on finite state machine models. These are the type of models that can show us the behavior of systems. And in our case, the systems are cryptographic protocols. So we want to show and to check the behavior of those protocols. And we'll be using model checking. Model checking are those tools that help us analyze those finite state models. And this is not to be confused with model learning. Model learning, if we have the time, this is in the advanced section. I'll mention that, and I'll also mention how we can combine model learning with model checking. Can you hear me? I hope you can hear me. Okay. Check. Is it better? No. No, right? And now? Okay, I hope it's better. Is it better? Okay, again, they tell me that at the end that it's good. Okay, thanks. So don't look what he's doing here, though. So this is a bit embarrassing, right? later, after the presentation. So we're going back to the question: is this protocol safe? We just reviewed it, and actually it's not. And here's the story of this protocol. It's called Needham Schroder Public Key Protocol. It's quite a famous protocol. It was introduced by Roger Needham and Michael Schroder in 1978. And Gavin Lowe used model checker 18 years later and found the issue. So it was 18 years, it was really used. It was a very popular protocol that was used for 18 years until they found that it's actually broken. And they found it. Gavin Lowe used a model checker to find this issue. So what's the issue? This is a screenshot from a tool that we're going to look at later. It's called Avispa. Basically, the tool runs on the code, and let me see if this works. Yes. So it tells us that it's not safe, and it gives us the attack trace, and we can look at the attack trace over here. So basically what happens is we have an intruder. We'll talk later about this intruder. I'll mention it now in a very few words. The intruder for us is like an insider. We have an insider in our network currently. This insider is equal to any other user on the network. We call him intruder. So let's give it a name. Let's call it Charlie. Sometimes they call it Charlie because of the letter C. So we have Charlie here, and Alice wants to connect with Charlie because she thinks he's a legitimate user on the network. She sends, like the protocol tells us to send announce and her ID, and everything is encrypted with Charlie's public key. So now Charlie, what he does, instead of replying to Alice, he decrypts that message because he has the private key of himself, and he sends that message to Bob, encrypting it with Bob's public key. So he tells Bob, look, this is my nonce, which is Alice nonce, and this is me, which is Alice ID. Everything is encrypted with Bob's public key. Bob thinks he's talking to Alice, but he wants to make sure. The protocol tells him, send him this challenge. He sends the challenge, this is your nonce, this is my nonce. Everything is encrypted with Alice public key. Show me that you have the private key, right? This is the challenge I want to see to make sure that I'm talking to Alice. So now what Charlie does, very smartly, he sends that message as is. He cannot decrypt it. It doesn't have the private key of Alice. It just sends it to Alice. Alice thinks this is the reply from her request, from her first request. This is his response. So she said, okay, great. I got Charlie's nonce. He sent me my nonce. And then I just return his nonce, and it's encrypted with Charlie's public key. So now Charlie has the secret or the nonce of Bob, because Bob was thinking he was talking to Alice. He didn't realize that he's actually talking to Charlie. Charlie has his secret now. Okay, so from now on, Charlie's actually man in the middle between Alice and Bob. He can see all the communication and Bob is sure he's talking to Alice. Okay, so this is the break, and this is how we can find it using tools. We'll see a demo later on. Roger Needham said, is very famous cryptographer. He created several other protocols after that. And he said this quote, "Cryptography protocols are 3-line programs that people still manage to get wrong." Are these really 3-line programs? Let's see. This is the diagram of TLS 1.3. 1.3 is even simpler than 1.2 because they made some simplification. These are all components of the protocol. Behind every such component, we have a big part of the protocol itself. If we want, we can see even such a very small scenario part of the protocol. This is a scenario that is protection control for downgrade. You can see it's way more complex than the previous protocol we just saw. And again, I ask you the question: can you make sure that can you be sure that this is safe? This protocol is safe. It's very, very difficult, right? Do it manually. So what's the solution that we're suggesting? So we're going to talk now about formal methods, very, very little, very briefly, and model checker, what they are there. And the goal here is to prevent logical attacks. Basically, we want to detect design vulnerabilities that can lead to logical attacks. Here's the process. Let me see. Yes. So we start with the informal specification of Can you hear now? Yes. So how do we make it formal? We design a modeling language that is formal mathematical syntax. And we also define set of theorems, or these are the security properties that we want this protocol to comply with, okay? And we're going to check that. So we have this formal specification model now. And we push it into the analysis tool that we're going to see later. And on the other side, the analysis will take formal intruder model. So we have a full model of the intruder. And formal methods, they give us the possibility of what we call models composition. So we can compose several models together in order to see what happens on the interaction between those models. So we have now the intruder interact with our protocol inside this model checker, and basically the model checker check all the possible paths that the intruder interact with our model and see if all of those paths comply with the theorems that we defined here. And if they're not, we get in the output the full trace of what went wrong, in which trace there was an issue that it was not comply with our theorem. So what is model checker? Let's see if it works. You see that the sound didn't work before. I hope you hear it. Which movie is it from? The Avenger, the Infinity War, right? So when I saw that movie, when I saw that scene immediately in the cinema, I told myself, he's a model checker. I think you cannot get geekier than that, right? Watch a Marvel movie and think of model checking. So why I thought he's model checker? Let's see. Yes. So we have Dr. Strange, right? He says, I read it for you. I went forward in time to view alternate futures to see all the possible outcomes of this coming conflict. And Chris asks, how many did you see? 14,605 futures. How many did we win? 1. And if I bring it to our world now, so we have the model checker, which is Dr. Strange. I tried all alternate paths to see all the possible outcomes of this model. And the hacker asks, how many did you see? 40,105. How many can we exploit? 1. So we have one vulnerability in one possible path here. And of course, if we think of Thanos as the universe designer, the new universe designer. So he can use also the model checker to see if his universe is exploitable. In our case, if our design of the protocol is exploitable. And if there's even one path that can be exploited, needs to be fixed, right? So what are the goals of the model checker? Basically, it's exhaustive exploration of the possible behavior. It tries to get to a full coverage, verify each behavior against required theorems, as we saw before, through mathematical proofs. It can verify systems that are not finite space. So if we have system like the TLS 1.3, probably it's not finite. We can make them finite using some kind of abstractions. And once they have some issue, they can show us the counterexample or basically the fault trace. A few words on the intruder model. We're using Dolev-Yao intruder model. And this is the specification of that model. So our assumption is that the intruder is an insider. I work for CyberArk, and CyberArk, we always think of the attacker as an insider, so this goes together with our thought. So the intruder is an insider. The intruder has full control over the network. Intruder can play role of honest or normal principal like any other principal on the network. He knows the public data of the network. It can start any number of parallel, like any other user, parallel protocol sessions, and it can intercept any message on the network, and it can generate any new message using the public knowledge. So he knows the public keys, he knows all the participants on the network, and every other knowledge that is public available. But the assumption is also that the cryptography is secure. So we're not going to check the cryptography itself. So we assume that it's secure. Yeah, it will happen several times. I saw that it happened to the previous speaker as well. So it's not me, it's not personal. So the intruder cannot encrypt or decrypt any message that if it doesn't have the keys. It cannot guess a secret or key because we assume that the random is perfect, okay? So it cannot guess those keys or nonces, etc. So let's view two analysis tools. We have the Avispa and the Tamarind Prover. So for the Avispa, I will show it using a Google Summer single sign-on vulnerability that was found using that tool, actually, by researchers. Everything I will show you today is not research that, those findings are not found by myself, found by other researchers. I cannot show you the things that I'm working on, but I show you very famous and very interesting other findings. So this is the message on availability they found using this tool. Let's look. So now it's demo. I have to sit. I'm sorry. So span is basically the UI of the Avispa. So we have the tool over here, and we're going to open this model now. You have the asymmetric one. And basically, first, let's see the protocol simulation itself, what the protocol looks like. So I'll do it very quickly. It's quite complex. These are already complex protocols. We don't have the time to really go deep and explain each step, but I'll try to explain it. I hope you will understand it. So this is a simulation that Avispa and Span Avispa let us do on protocols. Basically, we can start. This is the first message from a client to a service provider. Okay, so we're talking about SAML here. So the client sends to a service provider, look, I'm client. You are the service provider. This is my nonce. Everything is encrypted with the service provider public key. Okay. Service provider replies, okay, this is me, the service provider. This is your nonce. This is my nonce. Go to this IDP over there, and I sign everything with my private key, and I encrypt everything with your public key. All right, looks good, right? Client goes to IDP now to get the token, right? We're talking SAML. So client goes to IDP. This is my nonce. This is the service provider's nonce. I want to talk with this service provider. Please give me the token. IDP check if this client has the permissions to get to that service provider. If he does, sends the token. You are the client. I'm IDP. This is the service provider. Everything here is signed with the IDP private key. This is, again, your nonce. And everything, again, signed again, and then encrypted with the customer, with the client public key. And now the client goes to the service provider who looks, this is my token. I got it from this IDP. It's signed with this IDP private key. Everything looks really, really good. This is your public key. This is me. This is you, whatever. And everything goes well, and it gets the resource from the server, right? Looks very, very good protocol. It's very difficult to find the issue here just by looking at the protocol. You really have to use tools to actually find issues with such looks so good protocol. So what we do now? We have, Avispa gives us 4 different model checkers to choose from. I'm not going to describe and explain how model checker works. It's a lot of math inside. I actually was a developer of an open source model checker it was a project that was managed by Microsoft and the University of Washington. It was very interesting. I learned a lot from this project. So we're going to choose one. Let's choose this one and run the model checker on it. And it tells us here that this is an unsafe protocol and attack found. And over here, it will give us the attack trace. So we have the whole trace. And now the span tool give us let us actually review it in a UI. Okay, I hope it works now. Yes. So we can you hear me? Okay. So we have 2 options here. We can do the simulation as I just did before with the intruder now. It takes time. I'll skip that. We'll just go ahead and look the attack. Okay, so this is the attack. Takes a few seconds. There it is. So this is the attack. It's quite complex. I'll explain you why, and we'll not go too deep into it, but I'll explain the attack in words. What we see here is the tool generates several sessions in parallel. So we see here more than one session, because sometimes they also want to check what happens with several sessions interact with each other. In this case, what happened is that the intruder, very smartly, played the role of a malicious service provider. So the client connects with this malicious service provider. And and then why he did that? The reason he did that is because this intruder wants to get to a real service provider that it doesn't have permissions to access. So he makes the client connect with him. Using several steps here, he managed to rule or to lure the client to go to the ITP, give him the token. He takes that token, and now he is the client, go to the real service provider and gets permission there. So this is a really nice attack, and elevation of privilege, and also spoofing as a service provider. Really, really cool. We'll not go too deep into this because I'm really afraid that I don't have enough time. So this was Avispa. Let me think, yeah. We can go on now to continue with our lecture. So next we're going to look at Thermal Improver. Avispa is quite an old tool. Thermal Improver is considered to be the current, one of the most advanced tools in this area. It's been developed It's still being developed today. And it was used to analyze TLS 1.3. So TLS 1.3 is the first TLS protocol that was really analyzed and checked using model checkers. And there were several generations there that the model checkers all the time found issues. They fixed them. There were really nice issues that they found. And you could see it's really difficult to analyze this manually, but those model checkers did a great work. So at least the design of the TLS 1.3 is supposed to be or should be good. Of course, the implementation is a different story, and we'll look at the implementation in a few, if we have the time, a bit later. So for the time improver, I want to show you an interesting protocol that is run on still not, because we still don't have those networks, but this is the design of protocols for the future of when we have full roads with connected vehicles. So VANET is the vehicle ad hoc network. So, and it's part of V2X. V2X is vehicle to other vehicles or to infrastructure communication. And what we were going to look at is the revocation protocol. I'll explain to you in a minute what is the revocation protocol. So when we talk about VANET, this looks like a VANET. Basically, we have vehicles that connect ad hoc to a network. They form a network while they drive with themselves, with the infrastructure, because they continue and each vehicle goes elsewhere. They disconnect from the network, and then they form another ad hoc network with other vehicles or with other infrastructure. And also, they pass messages from each other. So if the infrastructure sends a message to one vehicle, it will go to all the other, so each vehicle will send that message to all the other vehicles. So they also, it's a form of peer-to-peer messages sending. So what we're looking here is this system of making sure those vehicles are allowed to join those networks. So we begin with the certification authority. Each vehicle has to obtain a certificate from the CA, okay? And then you can go to provider pseudonyms. What are pseudonyms? Pseudonyms are temporary certificates. So the certificate from the CA is a long-term certificate, and the pseudonyms are very short-term, very temporary. Why we need that? Because we want to keep the privacy of the drivers. So if you have one certificate and you use it all the time for all your communication with each network you connect with your certificate, it's very, very easy to follow you, right? I know every time I know it's you because this is your certificate. And now with all the GDPR issues and stuff like that, we really, privacy became a huge concern. And also with the connected vehicles, it became very important. So we want to keep privacy of the drivers and the vehicles themselves. So one way of doing that is using pseudonyms. So each vehicle, once they are allowed to use this, because they have the certificate, they will get a bunch of pseudonyms. This can be like a bunch for 2 weeks or for a month. Gets lots of temporary certificates. Each certificate like that, each pseudonym will be used for one drive, or even sometimes they will even can replace the certificate during the drive, and it will be deleted. So you don't use that pseudonym twice. So this will enable them to connect to networks and to communicate with the infrastructure or other vehicles. But we also want to make sure that we don't have malicious vehicles inside those networks. And the vehicles will have, each vehicle will have also like an intruder detection or malicious detection. So when a vehicle connects to the network and this intruder detection thinks that there's another vehicle that does some kind of funny things in the network, some spoofing attacks or try all kind of stuff, it immediately will send a report to the revocation authority. Look, this pseudonym is malicious, okay? So now the revocation authority, it will have some kind of threshold, like let's say after 3 reports, I'm going to revoke this vehicle, okay? So I'm going to revoke the pseudonym because the revocation authority is not connected with these authorities. It doesn't know the privacy, it doesn't know the vehicle itself, it just knows the pseudonym that was reported. So it will send a message, look, this pseudonym should be revoked. Now, As I said before, the pseudonyms are replaceable. What will happen is that each vehicle will also have a trusted component inside, which is hardware. It's like an HSM, something that everything is encrypted inside. If you try to break it, immediately it will delete the key, so you cannot do anything about it. And this is a trusted component, so the message will get to the trusted component. Once the trusted component gets that message, it see that it's his pseudonym. It will revoke all the certificates, all the pseudonyms that inside that trust component, okay? And then this whole vehicle is being revoked. So this is the protocol. It had several generations, and it was really nice to see how they check those generations using formal methods, using model checkers. I'm going to show you only one. I thought it's one interesting of versions of this protocol using the Tamarind tool. By the way, it was actually tested with this tool, so I'll show you the model that they created, the researchers created, and I hope we'll have a bit of time to go through the model so I can explain how the model looks like, what makes it a model. So what we're looking at here is those two messages. We have the message, basically order for self-revocation request. This is the message that the revocation authority sends to the vehicle, revoke yourself, right? This is revoked. This is your pseudonym that was reported. This is the reason, and everything is signed with the private key of the revocation authority, so it knows that this is a legit request. And each vehicle, as I said before, they get the message, they check, is this me, is this my pseudonym? If not, they send it to the other vehicles surrounding it until the one that really has that pseudonym will get it and will revoke itself. And now we have the confirmation message. I revoked myself, and this is a token that is part of the pseudonym. It sends it back to the revocation authority. Here, this is me. I revoked myself. This is proof because I managed to decrypt that pseudonym, and I extracted the token, and here's the token. So this is a proof that I really was the right one who revoked. The issue here, and this is the miss that in this version of the protocol, that they encrypted everything with the vehicle private key. This is the vehicle private key. And if you remember, the revocation authority doesn't know anything about the vehicle. It just knows the pseudonyms. So it actually doesn't have the public key of the vehicle, and it cannot check the confirmation, okay? So this is what we're going to look now. Let's look at the tool. Let's see how it looks like. So first, let me open here the model. We're talking about this version, okay, our token. So this is how a model looks like. We call it a theory, and then what we have here, these are the rules. Rules are basically the finite state machine states and transitions. So we have the first state. This is a constrained state, or what we call also a premise, and then the conclusion is after the 10 minutes. The conclusion is after the transition, which means it's in a new state, it's passed to another state. So we have those rules basically describe the protocol in a state machine. And then what we have here at the bottom, let me show you just one rule here. Which one? This is let's look at this one. So this is the request for revocation. We can see here that the request for revocation was sent, and there was some process here, and this is the confirmation. The next state is I'm sending back the confirmation. Okay, so we can see here, this is basically the vehicle got the request message, and then he sent the confirmation. Okay, so this is how it looks like. We have here all kind of restrictions. This is the abstraction I mentioned before to make the protocol something that we can that is not infinite state. And then we have dilemmas. Dilemmas are actually the proof. This is what we want to prove. So we have all kind of proof that now we want to check this model against. What we have here, one proof exists trace, is basically, this is sanity. We want to make sure that the model actually, at least one trace that it actually works. Okay, so this is a sanity check. And all the rest are really check all kind of proofs. Is it secure? Is it secrecy? Whatever. Let me open the tool itself. So we have a nice UI for the tool. So we're talking about this protocol over here. It takes a few seconds. Just work on it now. There it is. So what we see here, this is the lemmas. These are the traces. When we see green, it means it passed. It means the test passed. The lemma was good. This is the one that I told you as a sanity, so the protocol works as we at least thought it should work, and we described in this lemma. Over here we see red, meaning this lemma failed. And this was supposed to be at least one trace that it failed, meaning we have some kind of exploitable trace here. And let's see how it looks like. This trace, I hope, because of yeah, it's a bit big. So I'll try to make it a bit smaller. So we have the whole trace. It's because of the screen here, it's a bit difficult to follow. But we have the whole trace, and the one I wanted to look at here. Okay, you can do it here. These are the states, basically. What we see from one state to the other state, and we see the transitions. We see there are more than one scenario. We have parallel scenarios that go together, and actually we got to this state over here. So we have two scenarios. One goes okay. There was a report over here. There was a request for revocation, and this was accepted, the request for revocation. And this one sent the confirmation message. And this over here, what we see in round circles here, this is the intruder. This is the attacker. So the attacker has knowledge. This is the red arrow here tells us he knows this information here because this is public. Basically, he knows the message. He doesn't have to decrypt it or encrypt it, anything. Basically, he creates a new message. He sends it back because the revocation authority doesn't have the way to check that message. Basically, it will accept it. And what happened here is that we managed to tell the revocation authority it's revoked, but actually it was not. Okay, so it's like a spoofing attack, basically. Let's go back to the presentation very quickly. So model learning, this is another thing. Model learning is something that is reverse engineering. We run it on the implementation. So we have implementation. This is like a black box testing. It checks the implementation and creates the model. So it fuzz, it sends some information, it gets back, and it creates the behavior, a model of the behavior of the application. So we can use that, and it was actually used to find this issue in the secure socket of Java 1.8. Model learning managed to find, an issue in the implementation of Java. So this is really to check implementation, not design as the model checked before. Let's see how we can interact those two methods together. This is very, very interesting, very, very cool, very new field. Currently, I know that it only happens in the academics, but I really think that we should use that as well. So we have implementation, the model learning learns the implementation and creates a model learner. So we have now the model learner. We can use the intruder formal model from before into the analysis tool, and we actually can check now the implementation, right? Another thing is that we can use the formal specification model that as we created before, and we can compare it with the formal learner model, which is the implementation. So we basically compare the specification to the implementation. And here, this is what they did, these researchers, and they found actually issue here that with TCP or Windows 8, that it was not conformed with the specification. Okay, so this was a really nice find. By the way, using that way, you can create models for any component. So you have a model for client, Windows 8 client, Linux server, and whatever, and you can combine between them. You can check and test all those combinations. So for summary. So analysis of cryptographic protocols using formal methods and model checkers is a very complex and requires steep learning curve. Okay, so this, I showed you down, but it's really, there's a lot to learn to do. If you want to go into that field, there's a lot of learning to do. But I think this is necessary because security protocols are excellent candidates for rigorous analysis. We saw before. These are huge systems. It's almost impossible to test them and to check them by hand. And if you want to be a researcher and to find issues, I think you should go for model checking. Sometimes those protocols are critical in our systems, and sometimes they even look like the Google one. The Google looks very, very good. Nobody thought that it's going to be, there's a vulnerability there, but actually there was, and only tools could find it. That's it. We have 1-2 minutes for questions. So until you think of your question, if you want any more information, if you want, you have it. The model learner. Yeah, because we're talking about randoms. It's checking behavior, okay? So it creates a model of the behavior. So random is not really behavior. It will not check that kind of implementation. It will check only logical issues. And then all those models are pure logical issues, okay? Any other questions? Okay, so if you want to learn more, if you want to try it at home, you want some help, these are my contacts. I will be happy to talk with you to help you further. Okay?
Before you go, okay, you want to take a selfie challenge?
Yeah, sure.
Selfie.
Selfie.
Anybody that doesn't want, cover yourself.
Cover yourself, guys.
To the side real quick.
Selfie, yeah. I'm not using it so much.
Yeah, selfie.
Yay! Thank you, guys.